Welcome to next lesson in WKB approximation. In the last class, we have derived the probability of tunneling through a potential barrier by using WKB approximation. Here we will apply that tunneling theory for the explanation of the decay of alpha particle from heavier nuclei. So this is called the Gamow's theory of alpha decay. As you know, alpha particle is equivalent to helium nuclei, and they are spontaneously emitted from some heavy unstable nuclei. And the emission of alpha particle cannot be explained by using classical mechanics, because once the alpha particle is outside the nucleus, the potential barrier which is felt by the alpha particle to escape from the nucleus to the outside is of the order of 35 mega electron volt. But the energy of alpha particles emitted by various nuclear species is in the range of 4 MeV to 8 MeV. So there is a wide difference between the energy of alpha particle and the potential barrier that has to overcome by the alpha particle. So this cannot be explained by using classical mechanics. It is a clear example of tunneling through a potential barrier. So outside the nucleus, the alpha particle feels an electrostatic potential energy of repulsion between the nucleus and the alpha particle, which is given by V equal to 1 by 4 pi epsilon 0 2 Z E square by R, where 2E is the charge of the alpha particle and ZE is the charge of the remaining nucleus. Remaining nucleus means the daughter nucleus. So here Z is the atomic number of daughter nucleus. In some textbooks, if Z is taken as the atomic number of parent nucleus, then the formula will be 2 into Z minus 2 E square by R. Here in this textbook, we have taken Z as the atomic number of daughter nucleus. And inside the nucleus, alpha particle is bounded by the strong nuclear force. So the energy of the alpha particle is emitted is less than the peak of the electric potential energy. The potential energy curve of the alpha particle is approximately given in this diagram. Here we can see that the potential energy is negative because of the strong nuclear force. So this is the nuclear potential region, which extends up to a radius of R1. So small r1 can be taken as the radius of nucleus. And outside the nucleus, the alpha particle feels the Coulomb repulsion energy, which decreases as 1 by R, and we can see that at a distance R2, the total energy of alpha particle, which is represented by the dotted line, which meets the potential energy curve. So at this distance R2, total energy E is equal to potential energy. So this R2 is a classical turning point. So the region between R1 and R2 is called the tunneling region, and we have to integrate the magnitude of classical momentum over this region to find the transmission probability. And the typical values of these potentials, the peak value of electrostatic potential is of the order of 35 MeV, and the nuclear potential is of the order of minus 35 MeV, and the typical values of alpha particle energy is 5 MeV. Generally, nuclei are emitting alpha particles having energies from 4 MeV to 8 MeV. Clearly, this 8 MeV is much less than the 35 MeV. So, classically, alpha particle cannot escape from the nucleus, but experimentally, alpha particles are escaping from the nucleus. So, this emission of alpha particle can be explained only by using quantum mechanics, and it is an ideal example of tunneling of a particle through a potential barrier. And in fact, historically, this tunneling theory is one of the first method which was applied for the nuclear region using the quantum mechanics. So when the alpha particle is at the distance R2, the potential energy becomes equal to the total energy. So the potential energy at distance R2 is 1 by 4 pi epsilon 0 2 Z E square by R2, which will be equal to E. Now the non-classical tunneling region exists from R1 to R2. So the probability of tunneling per collision means the alpha particle is constantly moving inside the nucleus, and within well interior of the nucleus it is not experiencing any force, any net force. Once it reaches the wall of the nucleus, it will experience inward pull, so it will go back to the interior of the nucleus, so it feels what is called a potential barrier. But each time it collides to the wall, there is a small but definitive probability of tunneling, and the probability of tunneling per collision is obtained in the previous session by using the WKB approximation. It is T equals e raised to minus 2 gamma, where gamma is equal to 1 by h cross integral of the magnitude of classical momentum over the non-classical region or over the tunneling region, that is from R1 to R2. So here it becomes 1 by h, we have to find gamma 1 by h cross integral R1 to R2 2m into v minus e dr, that is equal to integral R1 to R2 root of 2m into v is 1 by 4 pi epsilon 0 2z e square by r minus e dr. Now this quantity 1 by 4 pi epsilon 0 2z e square by r can be written as 1 by 4 pi epsilon 0 2z e square by r2 into r2 by r. Now this 1 by 4 pi epsilon 0 2z e square by r2 is the total energy E, because it is the potential energy at the classical turning point. So that can be written as E into r2 by r1. So our expression becomes 1 by h cross integral r1 to r2 root of 2m into e into r2 by r1 minus e into dr, and it becomes root of 2m into r2 by r minus 1 into dr. And this can be integrated and exact solution is available. Integrating, we get gamma equal to root of 2m e by h cross into r2 pi by 2 minus sin inverse root of r1 by r2 minus r1 minus root of r1 into r2 minus r1. Now we are going to apply another approximation. The approximation is typically the nuclear radius r1 will be much less than the second classical turning point r2, and using, so this r1 by r2 will be very small. If theta is very small, sin theta is approximately equal to theta. So we can take sin inverse of root of r1 by r2 is approximately equal to root of r1 by r2. Remember, if inverse in the case of if for example if x is equal to sin theta, then theta equal to sin inverse x. If x is very small, if theta is very small, x is also very small, x is equal to theta, so theta will be equal to x. So we can apply in the sin inverse also. So gamma is equal to root of 2me by h cross into r2 into pi by 2 minus this one becomes root of r1 by r2 and multiplied by r2 it becomes root of r1 r2 minus root of r1 r2 minus r1 square, and this r1 square can be neglected when compared with the r1 r2. So we get root of 2me by h cross into pi by 2 r2 minus 2 into r1 by r2. Now that is root of 2me by h cross into pi by 2 into r2. The value of r2 is again using this formula. Using this formula, we get R2 is equal to 1 by 4 pi epsilon 0 2z e square by capital E. So it is 2z e square by 4 pi epsilon 0 E minus 2 into R1. R2 is 2z e square by 4 pi epsilon 0 E. That is equal to, we can see that this becomes e square by 4 pi epsilon 0, that is taken here. Then there is a pi. Then root of 2m by h cross, and this 2 and 2 gets cancelled, and there remains z by, here there is e, here root e, so z by root e minus here 2 root 2 and root 2 becomes 2 into 2 becomes 4, and there is another inside the square root, there is e square by 4 pi epsilon 0, so root of e square by 4 pi epsilon 0, then 2 into root 2, that is 4 root m by h cross, then root e and root e gets cancelled, there remains root of z into r1, so root of z into r1. So when we are looking this equation from various radioactive nuclei, The various radioactive nuclei will have different Z values and different energies for the alpha particles emitted. All other values are almost constant. So we can take, because E square by 4 pi epsilon 0 pi 2 m, m is the mass of the alpha particle, everything is constant here. So we can take this one as some constant k1. So this becomes k1 into Z by root of E minus k2 into root of Z R1, where R1 is the nuclear radius and Z is the atomic number of the daughter nucleus, where K1 and K2 are given. So the probability of transmission per collision is T equal to e raised to minus 2 gamma. Now the probability of transmission per unit time can be obtained by multiplying this collision probability the probability of transmission per collision into the number of collisions per second. For that, if v is the speed of alpha particle and r1 is the nuclear radius, then for conducting one collision, the alpha particle has to move a distance of an average of 2r1, that is the diameter of the nucleus. So over a distance of 2r1, it will make one collision. If it is moving with a velocity v, the time required will be, see, if v is the speed of the alpha particle, then the number of collisions with the wall per unit time will be v by 2r1. It is the number of collisions per second. So the probability of transmission per second will be v by 2r1 into probability of transmission per collision. That is v by 2r1 into e raised to minus 2 gamma. So the lifetime of the parent nucleus will be inversely proportional to the probability of transmission. So the lifetime of parent nucleus tau is equal to the inverse of this probability, that is equal to 2r1 by v into e raised to 2 gamma. That is equal to 2r1 by v into e raised to 2 into gamma. If we plot log tau, that is lifetime of the parent nucleus, against E, the energy of the particle, we get points on different straight lines for different Z values. Here you can see it is log tau will be equal to log of this one into this plus this quantity. From this we can see that the thorium, for example, thorium which has an atomic number of 90 will give one straight line. These dots are for different mass numbers of thorium, that is for the different thorium isotopes, and here also different points are obtained for uranium nuclei which has an atomic number of 92 and various mass numbers. So from this example from this expression we can see that the energy of the alpha particle and lifetime of the parent nucleus are extremely dependent. For example, if the energy of the alpha particle is 4.08 MeV, which is possible for some experimentally observed radioactive nucleus with mass number 232, the half-life is found to be 4.4 into 10 raised to 17 seconds. For example, but 8.95 MeV, that is highly energetic alpha particle, the half-life time is only 10 raised to minus 5 seconds. So as the energy of the alpha particle increases, the lifetime of the parent nucleus decreases drastically. The lifetime has a variation of about 10 raised to 22 when the energy of the alpha particle just doubles from 4 to 8 or 4 to 9 MeV. So the half-life is strongly dependent on the energy of the alpha particle. Highly energetic alpha particle has more probability of transmission, whereas low energy alpha particle has less probability of transmission, indicating long half-life time of that type of nuclei. All these are experimentally observed, and this was one of the first instances in which quantum theory was successfully applied in nuclear field. So this is historically very important, as the Gamow's theory of alpha decay it established the validity of quantum mechanics in nuclear field. Thank you for watching this video.